You should like today's lesson because, quite honestly, there's nothing new. Instead, we're just going to take a few moments and notice some perfect patterns. I may have actually renamed this perfect patterns. They're special because they're perfect. Nice thing about special perfect patterns is that they end up having some special shortcuts that allow us to make some quick work of that factoring. Now, remember, factoring is when you're doing a problem backwards, but sometimes it's helpful to do the problem forwards. That is, to multiply the problem so that we can maybe think about how we can reverse that process. So here we have x minus 3 squared, and, well, if you're saying that you know how to do this, good, but I still want to remind you that you don't do this. Were you thinking of distributing the square? Yeah, that's not a good idea. That's actually a math teacher's nightmare. Instead, you want to interpret the square as simply x minus 3 times x minus 3. You want to interpret that as a multiplication problem, because then we can actually do this multiplication. Some people call it the distributive property. Some people call it the FOIL method. Whatever you call it doesn't matter, but get my act together here. Let's multiply x times x and get x squared, and multiply x times negative 3 to get negative 3x. Well, you continue to distribute or multiply or do the FOIL method, and you take negative 3 to get negative 3x, and then plus 9. I know, we've done this problem before, but there's something special about it. There's something special about the type of final answer that we get when you combine your negative 3x's as well as record your entire x squared minus 6x plus 9. Let's look at another one, though. Might make it a little bit easier before we get ready to recognize the pattern. 2x minus 7 squared, right? 2x minus 7 times 2x minus 7. Once again, distributive property, FOIL method, whatever you like to call it, but you're going to distribute or multiply 2x onto both of those, and then you're going to multiply negative 7 onto both of those. So we have 4x squared minus 14x minus another 14x. Looking a little special, right? We end up with those two negative 14x's being negative 28x. Don't forget about your plus 49 at the end and your 4x squared at the beginning. Now here's the thing. Do we realize that you can take this answer and you can turn it back into these factors? Well, you will notice that once you realize that 4x squared was perfect, 49 was perfect. Both of them came from interesting numbers. They came from 2x and 7. And you see how 2x and 7 can help us to end up with 28. In this problem, technically negative 28. Same thing over here. X squared minus 6x plus 9 can turn back into these factors. That's because it's perfect. In a way, the x squared, it came from an x. The 9, it came from a 3. And you see how 3 and x can help us to eventually arrive at this negative 6x. Well, in a moment, we're going to talk about that pattern. But let's look at two other problems. Kind of nice to just do all these problems. Do you notice that this is different? That would be helpful. Do you notice that this is 2x plus 7 than 2x minus 7? Yeah, there's a plus and a minus. Now, when you have a plus and a minus, then one of your terms ends up being the opposite. That is, these 14x's end up being the opposite. And, sorry about that. I made a mistake. 2x times 2x, that's 4x squared. 4x squared. I was so concerned about these negative 14x's being opposites that are going to cancel out. And we end up with just 4x squared minus 49. Now, 4x squared minus 49 is also perfect, and it can turn back into these factors. So is it going to work here? It should work. Okay, we're going to end up with an x squared. We're going to end up with a minus 4x. We're going to end up with a plus 4x and a minus 16. Are you already ready just to cancel these 4x's and just write x squared minus 16? That's because this is a perfect pattern. This came from an x. This came from a 4. All we have to do is realize how to turn them back into these factors. And we'll do that by looking down here at our two rules, our two special rules for today. You're always going to end up with a certain pattern, a pattern that you can definitely see from using A's and B's. And that pattern is that, well, if I distribute all of these, I'm going to get an A squared. I'm going to get a B squared. But it's this number in the middle we want to recognize is always like having two of the ABs. So I get A squared plus 2AB plus B squared. Well, it works that way when it's subtraction. In other words, I'm going to get my A squared and I'm going to get my B squared. But this time I'm going to get two negative ABs. So minus 2AB. And we typically call that the term in the middle. So when I have this form, when I have A squared plus 2AB plus B squared, or A squared minus 2AB plus B squared, we call that a perfect square trinomial, sometimes abbreviated PST. What's a perfect square trinomial? Well, again, it's always going to look like a perfect square number. That's kind of like my A squared. So it's going to be like a perfect squared number. There's always going to be another perfect squared number at the end. And by the way, it will be always added. It's this number in the middle that we want to realize is like having twice, it's like having twice the product of A and B. It's twice the product of A and B. And when you have that, again, we call that a perfect square trinomial. So what are we going to do with that? Well, we're going to find out that if you factor these, which would be like taking our answer and going back to where we started, if I factor these, well, yeah, they're always going to factor into two binomials that look the same, whether they look like x minus 3, or whether they look like x plus 4, they're always going to be the same. How about the last two that we did here? The last two. Did you guys realize that these were actually special because they had a plus and a minus? And when you have a plus and a minus, look what kind of answer you get. Yeah, you always get an answer that involves perfect squares and a subtraction sign. And we call that a difference of squares. How can we simulate that with like A's and B's? Well, again, if I do the distributive property here, I realize that my term in the middle is going to cancel out. And since that term in the middle is going to cancel out, I'm only going to be left with an A squared and a minus B squared. And again, when I have an A squared and a minus a B squared, we call that a difference of squares. It's basically going to be, once again, perfect numbers with a subtraction sign between them. So what am I going to do with this? Okay, well, again, we're going to try to factor. Now, here's the good news. You really don't have to do anything different with your factoring. It's more realizing that, okay, I might end up with a special answer, and sometimes if I get a special answer, maybe there should be an extra step that I could do at the end. But let's kind of look at this x squared minus 4x plus 4, and let's just kind of look at this, well, maybe without anything special. You say, well, how do I look at it without it being special? Well, like we did on the very first day. You just factor it by looking for two numbers that multiply to be 4 and add to be negative 4. Wait, multiply to be 4 but add to be negative 4? Yeah, that's going to be like x minus 2, x minus 2. So what just happened here? We got two binomials that look the same. Yeah, that's because they can be written as x minus 2 squared, which means that this thing I started with, this x squared minus 4x plus 4, it was a PST. It was a perfect square trinomial. You say, I don't get it. Well, look, I've got a perfect squared number. That's my perfect square. I've got another perfect squared number. Now, the number in the middle comes from thinking of these perfect squares, thinking of where they came from. And yeah, they came from the number 2, or they actually came from like a 2x. And so I have twice of those. I have 2 of those, and 2 of those 2x's are going to give me 4x. You say, I don't know if I really want to think that way. Well, you don't really have to be honest. You can do the problem without recognizing that it's a PST. But it doesn't hurt. It doesn't hurt to kind of realize that some problems just don't have the right look. You say, what do you mean it doesn't have the right look? Well, the number that 1 came from, yeah, it had to come from 1. Basically like a plus 1 and a plus 1. Now, wait a minute. That's not going to work because this 4 right here, this 4 isn't like twice the product of 1x and 1x. Yeah, the product of 1x and 1x is just going to be 1x, and twice that's only going to be 2x. The point is that this problem was not a perfect squared trinomial. It just didn't have the look. I couldn't actually break it down into x plus 1, x plus 1. And I can't break it down into anything. And that's why it's disappearing before our very eyes, so that we can say that this problem is prime. Prime means that it cannot be factored. It's just not going to work. It doesn't have the special look, and there's no way that I can come up with the factors. So now what am I going to do? Well, what you're going to do with a problem like this, you're going to realize that we've got some special numbers going on here. Like 49. Do you agree that 49 came from 7? 7 squared. And x squared, it came from an x. How about this 4y squared over here? Where did it come from? Well, it came from a 2 and a y. Now, it looks like that these numbers, if I put them together, if I multiply them together, I'm going to get 14xy. Now, is that equal to 28? Well, no, but twice this product is. You see, what's happening here is this problem has the look. It has the look of a PST. In other words, I can actually factor this problem to be a 7x plus 2y and a 7x plus 2y. Better said, a 7x plus 2y squared. Again, it worked because it was a PST. It had the look. Do you think you can do that to a problem like this that appears to have lots of big numbers? Can you figure out where 36 came from? Where did x come from? Excuse me, x squared. Where did x squared come from? Yeah, it came from an x. So I can do the same thing with 25y squared. Now, if I think about multiplying these together, I'm going to end up with 30xy. But that's good because then you double it. Remember, you always need twice that product. And yeah, that's going to end up being 60. 60xy. What does that mean for 6x and 5y? It means that those are the terms that go in my factor. And if I want to, I can just say right away, 6x plus 5y, the quantity squared. Again, this one was a PST. Now, you got to look at letter E and say, that's not a perfect square trinomial. That's not 3 terms. Maybe it's a difference of squares. Maybe not. You see, it's not a difference. So it's going to be hard trying to say that somehow I can factor this. But what if you try? What if you say, well, wait a minute. 9x squared came from a 3x and a 3x. 16 came from a 4 and a 4. Okay. What happens if I start distributing, particularly these two parts right here? That's right, I'm going to get a 12x and another 12x. Oh, shoot, they're not going to cancel out. They're not going to cancel out because they're both positive 12x. Can I just maybe change one of these to be like a plus 4 and a minus 4? Well, then you're going to get your 12x's to cancel out, but then you're not going to end up with positive 16. You see, it's going to be like negative 16. And that's why you can't do it. You can't do it because it's not a difference of squares. It's a sum of squares, to be honest. It's prime. It's prime. You can't factor it unless it's a difference of squares. Yeah, when it's a difference of squares, you're in business. As long as 9x squared is a perfect number, yeah, it came from a 3x and a 3x. And negative 16, yeah, that came from a 4 and a 4. Specifically, a plus and a minus. Well, we just factored that difference of squares into a sum and difference. What do you think? Is it a PST? Does it have the look? Can we say that 25x squared came from 5x? How about 1? Can we say that that came from 1? Yeah, technically 1 squared. By the way, technically 5x squared. So yeah, 1 came from 1. Now if you multiply these together, you get 5x. But if you double it, which is what you're supposed to do, oh look, I do get 10x. Okay, now what this means is that this was a PST. I can factor it using 5x and 1, but another 5x and 1. In other words, it can factor to be 5x plus 1 squared. That's my cat, my wife's cat jumping around. If you hear a little rattle. X squared plus 2xy plus y squared. Did you realize that this is the formula? This is the formula for a perfect square trinomial. What that means is that this very clearly is going to just be the cat just rubbing its head up against everything. This is going to just factor to be an x plus y, and, well, that means x plus y squared. Letter H is the same as our a plus b formula. Okay, whether it's x's and y's or a's and b's, again, that's a perfect square trinomial. So, did we do something new today? Well, yes and no. Some problems will be perfect square trinomials. When they are, great. You can recognize that, and perhaps it can save you a few minutes. Or if you don't recognize it, you just kind of go on as normal, and you should still be able to factor the problem. For homework kind of practice before the end of the period here, we've got the why did King Kong eat a truck? Just a little riddle. You're trying to figure out which statements are true over here. And over here, we're just trying to figure out if we got PSTs. Yeah, they called it a trinomial square. I called them a perfect square trinomial. Same thing. All right. Keep up the good work.